So hello everybody, we are beginning with chapter 11. So the name of this chapter is Dual Nature of Radiation and Matter, and this is lecture 1. Dual nature of radiation and matter. So if we begin discussion on this, let us first of all talk about the things which we are going to come across in this chapter. So the first thing that we will be discussing is the electron emission process followed by photoelectric effect, and then we will be dealing with Broglie wavelength. So the first thing that we begin with in this particular chapter is electron emission process. Electron emission process, or we can say processes, because we will be dealing with different ways by which electron can be emitted. So there are various ways by which electron emission can be conducted or can be done. The first term that we come across is called as ionization potential. Now let us first of all understand this word ionization potential. So when we say ionization potential, it implies the minimum amount of energy that is required to remove an electron from the atom of an element. So it is the minimum amount of energy required, minimum energy requirement to knock out an electron from an atom of an element. Now over here there is a distinction between the word which we will be using in this particular chapter, which is work function. Work function and ionization potential is not the same thing. When we say ionization potential, I just mean to say that it is the amount of energy that is required to bring out an electron from the atom of an element. But when we will be talking about electron emission process, the word we will be using is work function. That is the minimum amount of energy required to remove an electron from the metal surface. So in this case of the ionization potential, we are trying to bring out the electron from the atom of an element. And when I talk about work function, then I define that is it as the minimum amount of energy required to bring out an electron from the surface of a metal. So it is defined as the minimum amount of energy, the minimum amount of energy required to knock out electron from a metal surface. So this is in where the distinction between the term ionization potential and work function is established. Now there are several ways in which we can supply this work function to the metal surface, and based on the ways we classify them in various categories. So let us discuss about them. So the various ways of electron emission. So we are seeing ways of electron emission. So when we say ways of electron emission, the first way is regarded as thermionic emission. So in case of thermionic emission, uh, a metal surface is heated, its temperature is increased, and with the temperature, the thermal agitation of electrons in the surface also increases. When the temperature of surface attains a value, that is when the agitation energy of free electron approaches the work function of the surface, These electrons starts coming out from the metal surface and constitutes a continuous current into the surface if the surface is maintained at that constant potential, and such a kind of emission is regarded as thermionic emission, or in short we can say that the electron emission which is facilitated with the help of heat energy is regarded as thermionic emission. Facilitated with the help of heat energy, with the help of heat energy. So I'm repeating one more time what exactly happens. On heating the metal surface, the temperature increases, and due to this, a thermal agitation of electron is produced. Due to the thermal agitation or the agitation energy of free electron approaches the work function of the surface of these electrons starts coming out from the metal surface and constitutes a continuous current into the surface if the surface is maintained at that constant potential, and such a thing is regarded as thermionic emission. So this is the first way that we have come across, and just for fact I can say that this work was done by Richardson-Duchemin equation. So it is explained using Richardson-Duchemin equation, and we write it as J equals at square e to the power minus 5 by kt. This expression is not a part of your syllabus, so you don't have to worry much about it. Where A is called as the Richardson constant, S is the surface area of the metal, that is, then the thermionic current at the surface can be written as I is equal to J into S. So there is no need to remember this formula. It is just written for the interest purpose. Let us come to the next aspect. So the next way by which the electron emission can be done or facilitated is called as field emission. So we call this as field emission. So in the case of field emission, what is done is that a strong electric field is applied. A strong electric field is applied generally of the order of 10 to the power 8 volt per meter, and as a result of this strong electric field, the electrons are exerted by the electrostatic force, and as a result of which the electrons are pulled out of the metal in a spark plug. So something like this is done. So a strong electric field, so it is facilitated with the help of a strong electric field, facilitated with the help of a strong electric field. So a very strong electric field is applied, and the kind of emission that takes place is regarded as field emission. The next one in the category that we are going to deal is regarded as photoelectric emission, and is a great part of our syllabus. So we say photoelectric emission. So photo means light. So the emission of electron that is taking place because of the electromagnetic waves. Rather than saying light, we will be saying electromagnetic waves. So the emission of electron is facilitated with the help of electromagnetic waves, which brings energy in the form of energy packets called as photons, and as a result of which the electrons are emitted. Facilitated with the help of electromagnetic waves or light we can say. So these are the three ways by which the electron emission is attained, and we will be discussing in great detail about the photoelectric emission. So right now I've just mentioned that the emission is taking place with the help of light, or basically electromagnetic waves, and that is regarded as photoelectric emission. So now let us begin with the fundamental laws of photoelectric effect. Fundamental laws of photoelectric effect. So I will be stating different points, and each point will make a contribution in the study of photoelectric effect. So the first thing is the things of historical importance. So on the basis of Planck's idea of quantization of energy, in the year 1905, Albert Einstein proposed this theory of photoelectric effect, and in the same year, Einstein also gave the idea of what is known as special theory of relativity. And we will be discussing about some points of photoelectric effect. And prior to that, it is equally important for you to understand that the study of photoelectric effect doesn't start with the Planck or Albert Einstein. It is rather starting with Hertz observation. So Hertz was the first person to have come across the observation, and he was the person who discovered it in 1887 by uh, observing that because of the electromagnetic wave that is striking the metal surface or illuminating the metal surface facilitates the escape of charge. These charge particles which we come across or we known as electrons. So this observation was first of all done by Hertz, and it was done back in 1887, which later on was explained, or the theory was explained by Albert Einstein in 1905, using Planck's idea of quantization of energy. So now let us begin with it. So the Hertz observation was there, and now we are talking about in point wise in according to what things happens in photoelectric effect. So the first thing that we say is when the light incident on the metal surface, so photoelectric effect starts or initiate only at a certain value of frequency, and this value of frequency is called as threshold frequency. Below this frequency, there is no emission of photoelectrons that is observed. So we say the emission of photoelectrons, the emission of photoelectrons or photoelectric emission takes place only above the threshold frequency, or we can say the minimum frequency, the minimum value of frequency at which photo emissions is observed is called as threshold frequency. So this is the first point that we write, and it is because of the work function of the metal. It is because of the work function of the particular metal, which we have already discussed. That is, I mean to say something like this. I mean to say something like this, that if phi is the work function, if phi is the work function of the metal undergoing photoelectric photoelectric emission, then I can say that the minimum value of frequency, that is h mu. So this is coming from the Planck's equation, that energy is written as h mu, and we are talking about the threshold frequency, so I'm writing it as frequency minimum. This must be equal to the work function. So from here I can say that the minimum value or the threshold frequency, which can also be said as the minimum value at which the electron emission starts, can be written as phi by h. So this can be written as phi by h, and this is called as threshold frequency, the minimum frequency of the light radiation which is required to eject a free electron from the metal surface. So the work function is basically energy. As we have already defined, it is defined as the amount of energy required to bring out the electron from the metal surface. So work function is basically energy, and this is the Planck's equation for energy, that is E equal to h mu. So which we have used over here, and I have already stated that the idea of photoelectric effect which was given by Einstein, so it was done on the basis of Planck's idea of quantization of energy, and the Planck suggested that the energy is quantized or occurs in the form of energy packets, such that the value of each energy packet is equal to h mu. The next thing that we define post this is the value of threshold wavelength. Threshold wavelength. So the wavelength corresponding to the threshold frequency is defined as threshold wavelength. The wavelength corresponding to the threshold frequency is called as threshold wavelength. So it is regarded as threshold wavelength, and we can say from here that the value of threshold wavelength can be calculated in this way, that from the energy equation for Planck we say that energy is quantized in the form of h mu. So if we use the expression mu can be written as c by lambda. From this equation, c is equal to frequency into lambda. So from here I can say that frequency is equal to c by lambda, which we have replaced in this particular equation. So if I equate this value, so for threshold wavelength, we can simply say that this energy, that is hc by lambda threshold, is equal to the work function, and hence the threshold wavelength can be written as phi by hc. So this is the wavelength corresponding to the work function, corresponding to the threshold frequency. Now the emission of uh, photoelectrons will take place for the frequency which is going to be, the energy of the incident will become less than the work function of the metal, and hence the photoelectric effect will not start. So for photoelectric emission to take place, the value of frequency must be less than threshold frequency. क्या कर रहा है ये लास्ट लाइन पूरा काट देना इसके बाद से. इस ब्रैकेट के बाद से थोड़ा गलत बोल दिया. And hence, as we are seeing that energy is inversely proportional to wavelength, so I can say the following, that for the wavelength of incident light, that is lambda greater than lambda threshold, the energy of incident of the photons will become less than the work function of the metal, and hence photoelectric effect will not start. So photoelectric effect will not start. Will not start. So for the photoelectric effect to take place, it is important that if we are talking in terms of frequency, then the frequency must be greater than the threshold frequency, but the wavelength must be less than threshold wavelength. The frequency must be greater than the threshold frequency, but the wavelength must be less than threshold wavelength. The next idea that we are discussing over here is, the next idea that we are going to discuss over here is, for energy that is greater than, for incident energy greater than the work function. So one thing is established, that if the incident energy is less than the work function of the metal, then no photoelectric emission will take place. So now we are talking about what if the incident energy is greater than the threshold frequency. So now, following the Planck's idea, Einstein suggested that the energy of photon, which is greater than the work function, so the absorption of energy will be done in two parts. So we say that it can be categorized in two parts. The first thing that is done over here, which I am writing as point number one, which is sub part of the third point, is a part of energy, a part of energy is absorbed, or I can say utilized, in bringing out the electron, in bringing out the electron from metal surface. And the second thing which I say is, the remaining part of the photon energy, the remaining part of the photon energy is absorbed by photoelectrons, is absorbed by the emitted photoelectrons, which appears in the form of their kinetic energy, which appears in the form of their kinetic energy. Now one very interesting fact is to be stated over here, which I am stating like this. So if we consider that this is a metal surface, which is having a work function of phi. Now there is a incident light over here, which is falling on this metal surface, and having energy E equal to h mu. such that this energy is greater than the threshold frequency or greater than the work function. So because of this, the photoelectrons will be emitted. The photoelectrons will be emitted. And when they will be emitted, they will have a certain value of kinetic energy. They will have a certain value of kinetic energy. So I write over here that kinetic energy maximum. Now there is a reason why I am writing kinetic energy maximum is equal to the incident energy, which is in the form of h mu minus work function phi. And this is the equation that won Einstein Nobel Prize. So let us understand why I have written over here maximum. What is the reason behind kinetic energy maximum? So what happens is in practical cases, whenever an electron absorbs a photon from the incident light, it comes out from the metal surface, that is for the energy h mu, which is greater than phi. But in the process of ejection, it may collide with the neighboring electrons, and before ejection, it may lose some energy during the collision with the neighboring electrons. And in this case, after ejection, the kinetic energy of the ejected electron will be certainly less than the value, that is ei minus phi. So it will be certainly less than the value ei minus phi. And obviously there will be some electron which will manage to come up with the entire value of ei minus phi, and they will have the maximum value of kinetic energy. And hence because of this thing that is taking place, that is the collision of the electrons with the neighboring electrons before ejection, we say that all the ejected electrons from the metal surface may have different kinetic energies, and it is distributed from 0 to this maximum value. So I write over here that due to the collision of photoelectrons with the neighboring electrons, all the ejected electrons may have kinetic energy ranging from 0 to kinetic energy maximum. That is, it is possible that all the energy is absorbed, or maybe say I can say got wasted in the collision with the neighboring electrons. So the next point which we are discussing over here, that is we have ended up discussing 3 points. So now we are coming to the fourth point over here. So the fourth point which we are going to discuss, so now I am writing a line, ideally, which do not happens, ideally each photon is capable of emitting a photoelectron. So this is something that is taking place with 100% efficiency. That is, if I say that there are 1,000 photons that is striking a metal surface or a metal target, then it can produce 1,000 photoelectrons. But it will only take place if the photo efficiency or the quantum efficiency of the metal surface is 100%. It is not the case. It is never the case. So over here I say that it is important that the energy of the photon incident on the metal is not necessarily cause the emission of an electron, even if its energy is more than the work function. It is to be understood over here that maybe that the photon is having the energy which is greater than the work function, but it may not be able to emit a photoelectron, and it is because of the quantum efficiency of the metal surface, which is not likely to be 100%, which is not likely to be 100%. And we say that we define a term that is quantum efficiency or photo efficiency, and it is given by number of electrons ejected from a metal surface to the total number of photons incident on the surface, to the total number of photons incident on the surface. So we define this in this way, and this term is called as photo efficiency or quantum efficiency. Now it is over here, it is equally important that as photoelectron increases, as photoelectron increases, I can say the value of photocurrent. Photocurrent is the current that is originating because of photoelectron. The flow of electron is regarded as current flow. Now since it is photoelectron, so we say that it is producing photocurrent. So increases the value of photocurrent, that is, we will understand this line later on. Saturation current increases. Saturation current increases. Now what is important over here is one more thing, that when I say that the number of photoelectron is increasing, I never mean to say that the value of the energy of photon is increasing, because energy is E equal to h mu. It is a function of frequency. So it is really important over here to understand the another fact, that as I say that the a large number of photons is striking a surface, a large number of photons is striking the surface. So it implies that the intensity of light is more. The intensity of light is more, or the intensity of electromagnetic wave is more. So it is important for you to understand that we can increase the intensity without increasing the energy of each photon. The energy of each photon remains the same. The energy of each photon remains the same because it is a function of frequency. We say E is equal to h mu. So it must be very well kept in mind that maybe I am using a small point source of light, and it is emitting, suppose, like 5 photons, each having an energy of h mu. Now I can use a bigger source of light, but the color of light is still the same, that is the frequency is still the same. So now this time this light is capable of producing maybe a large number of photons. So when I say a large number of photons, I mean to say that the intensity increases. So there is an increase in intensity. There is an increase in intensity, but the energy of each photon, that is h mu, remains the same. H mu remains the same. So there is maybe an increase in intensity. So over here we can say that intensity is less and over here intensity is more photons, less photons, and hence we say that it is capable of producing, over here I write low saturation current, I write high saturation current. It is really important for you to understand that this value of energy E equal to h mu remains the same. So if I write the equation kinetic energy maximum of the emitted photoelectron, then it is equal to h mu minus phi. So you need to understand that in this particular equation, in both the cases, the value of h mu is same, and so is the value of work function. So the maximum value of kinetic energy of the photoelectron that is emitted remains the same. The maximum value of the emitted value of kinetic energy of the photoelectron remains the same. The only difference is in this second case, or I can say B case, a large number of photoelectrons are emitted, and in the A case, lesser number of photoelectrons are emitted. But the maximum kinetic energy of the emitted photoelectrons remains the same. So on increasing the intensity, the only variation is the change in the photoelectrons, that is the change in the value of photo current, which we refer to as saturation current, but the value of stopping potential remains the same. And we will begin with stopping potential in the next lecture. It is important for you to just understand till now that the kinetic energy of the emitted photoelectron, that is the maximum value of the emitted photoelectron, remains the same in both the cases. The only thing that we have done is we have increased the number of photons striking the metal surface by using a source of more intensity.